So welcome everybody, and today we are going to discuss about a topic from an architecture perspective in light of performance. So my name is Ionut Balosin. I'm software architect. You can find more details about me on my website ionutbalosin.com or on Twitter. Apart the software architecture stuff that I do on a daily basis, I also conduct technical trainings, especially on the performance and tuning targeted to Java and on software architecture field. What is the agenda for today? I structured the current presentation in 4 layers actually. The first layer is about design principles. So we will go through a lot of design principles and we will study their implication from a performance perspective. The second layer is about tactics, patterns, data structures. So we will go inside this layer and we'll reveal other guidelines that we need to tackle when we design for performance, and we'll continue with the operating system guidelines, and the last one, more challenging one, is the hardware guidelines. So all of them from performance standpoint. And in regards to that, I've created my own latency hierarchical model, which basically maps the projects. So it consists of few layers, and it maps the project on each of these layers, depending on the latency you need to tackle in your applications. For example, if you have applications where the performance is not an architecturally significant requirement or an ASR, for example, you have applications where the response time could be within several seconds. You really don't care too much about performance, so this is the layer for that project. On top of it, it's the layer that corresponds to the projects where the latency is affordable, which basically means that you have a response time around hundreds of milliseconds. Then you have projects where you need to satisfy the ultra-low latency constraint. In other words, you have a response time within few tens of milliseconds, and the last one and more challenging one, the most challenging one, is the ultra-low latency systems, where you have to satisfy the response time within maximum 1 millisecond. So during this presentation, we will go through a lot of guidelines, techniques, patterns, and at the end, we will get back to this latency hierarchical model and we'll try to map them within this one. And based on your application, it's very useful for you because you can try to zoom in inside one layer which makes sense for you and it's applicable in your case, and use such guidelines. So this is the presentation about. First of all, before to start, it's better to define the performance. What is performance? And for defining the performance, I took a classical definition from a software architecture for software architecture in practice book. It's a very nice book, and I really encourage you to read that, which says that performance is about time and the ability to meet time requirements. So there's nothing else. If your time is several seconds or several milliseconds or several nanoseconds, but you fulfill that in your application, you can say your application meets this performance. A lot of people, when they refer to performance, scalability, availability, all these entities, call them non-functional requirements. And for me, as a software architect, it's a bit misleading. I also encourage you to not use non-functional requirements, but quality attributes. So quality attributes, it's a proper terminology or a proper term when you discuss about performance. And I wrote an article around 1 year ago. It is published by InfoQ, and I explain my rationale around why it's misleading to call these entities as being non-functional requirements. So my advice for you is to stick with quality attributes because they are proper quality attributes, non-functional requirements. So this is about the briefing about the introduction. Let's start with the first layer for design principle. And the first one, it's very simple. It's about cohesion. You know about cohesion from 70s, from 80s. If you read articles from that time, they really define cohesion in a precise way. Cohesion refers to the way the modules or the classes, packages, whatever components, they relate or work together. And also from a performance perspective, it's good to keep a high cohesion, as you can see in that picture, to group the elements that work together, to wrap, to package them together. From a performance perspective, it has a very big implication, because performance, it's about cohesion, sorry, high cohesion, it's about locality. Packaging things that work together, you create a better locality. Better locality also helps the CPU, the prefetcher, so you are more CPU cache friendly. And also it's valid for the instruction. For example, if within your class you have a lot of objects that are not cohesive, or a lot of methods that are not cohesive, when you call one method and you basically pollute the instruction cache with other instructions. And the same for data. So it's better to keep the things that are working together, to keep them located, because you benefit of the CPU, it's by hardware implicitly. Also, the things that are not linked together, they should be decoupled. Abstractions, Dijkstra said about abstractions that the purpose of abstraction is not to be vague. On the contrary, to create a semantic level within, you should be really, really precise. Abstractions basically are handled, as is in this diagram, are handled via polymorphism by virtual calls. Because, for example, you have a base class, which is the shape, and you have multiple implementations like rectangle, triangle, right triangle. And each of these, it's basically an implementation of an abstract class shape. And each of these override method getArea. During the runtime, if you have a base reference to the shape, but the implementation it's one of these, rectangle, triangle, or right triangle, the compiler itself needs to get the actual implementation. How the compiler does that? By devirtualizing the virtual call. And this devirtualize process takes time, so it's better to be very, very specific and to not abuse of these abstractions. I might agree that you create loose coupled components and so on, but from a performance standpoint, the advice is to really use it consciously without ending in too many abstractions. And particularly in Java, in hotspot, there is a limitation for that. 1 second. Okay, particularly the Java developers from here, starting with the third implementation, there is no any optimizations under the hood. So if you have more than 2 possible implementation for one abstract class, you pay the cost of virtual call all the times in hotspot in Java, because there is a limitation in the compiler itself. So be careful with the number of abstractions and use them consciously. It's a very good question. For example, when you have one target implementation, this is called monomorphic call, because you have just one possible target invocation. It's around 3-4 nanoseconds. If you have 2, it's 5, 6. If you starting with the third one, it's 9, 10. So basically, between starting with the third one, it's plus minimum 5, 6 nanoseconds per call, which I might say it's not big, it's about nanoseconds, but if you work on ultra low latency stuff, you really should be worried about that.
Yeah, but in everyday software, it's infinitesimal, it's very small.
Yes, in everyday software, yeah, if that's why I present you to the latency model, and depending on your context, you should apply or not this kind of tactic. 1 second, because I have some troubles with my output, still not working.
We're supposed to route it through here because
Okay. Okay, so I'll just keep talking. So the abstractions, it's covered. Psychometric complexity, we are on the design principle. Psychometric complexity, it's another one you should really be worried about that. What is psychometric complexity? It refers to the number of independent paths that your code can follow during the runtime. For example, if you have a method and you have a switch with a lot of cases, and or for example, if else, if else, if else, to minimize that, to try to mitigate that, because you also impact performance by the clean code, as I was saying. Okay, algorithms complexities. I'm here in particular, I refer to the BigO complexity. And we learn from high school, we learn from faculty, we learn all the times that BigO complexity really matters, because BigO complexity, it's about serviceability. So having a lower BigO complexity or BigO notation, implicitly you have quickest service time, or the server responds you quicker. However, let's see if this BigO complexity really is all that matters on modern hardware. And here I need the projector because I have some graphs to visualize. One second, sorry. Okay. By the way, until the things are set, who's the Java developer out of the audience? Okay, quite nice. C++ developers? Oh, that's interesting. And .NET? Okay, that's perfectly fine, because by the way, the presentation, it's not targeted to any particular programming language. It's about principles, guidelines that are useful whatever programming language you use. Actually, it's agnostic. Okay, so that's good. So we were here. So let's see if on modern hardware, how much it is about the BigO complexity and how much it's about the CPU caching effect. In regards to that, I took a very simple problem, the problem that basically traversed a matrix. And first case, it's traversing the matrix in a row fashion way. For example, I keep the same row and I change the columns. Versus the second one, when I keep the same column, but I change the rows. The code looks very simple. Basically, are two loops, one inner, and for the row traversal, you compute the sum. You basically iterate through all the elements and say matrix of I and j. As opposite, in column traversal, you say matrix j and y. Basically, you keep the column and change the rows, and here, for the row traversal, you keep the row and change the columns. In terms of complexity, it's O of n a power of 2. The same complexity for each algorithm. However, if you try to write some short benchmarks and you try to analyze for different matrix sizes like 64, 512, 1024, or 4K, the number of operations per microsecond, you will see that in all the cases for the row traversal, it's quickest, it's fastest, it's faster. And you can see it's around sometimes one order of magnitude. And the question is why? Because it's the same complexity. However, if you run these two programs, there is a discrepancy in terms of performance. It's not something marginal. Let's take the last one, the matrix size 4K by 4K, and see what really happens. Why is there such a noticeable difference, like one order of magnitude? But before really understanding what happens, I decided to profile the CPU. You can profile the CPU, for example, in Linux it's very easy, and you can also get the number of cycles per instructions, how many cycles for each instruction it costs, and also the number of cache misses for both L1 and last level cache. For example, last level cache, it's L3 cache. And also translation look-aside buffer. I'll get back in a second for the translation look-aside buffer. And having all of these stats, you can see as well that in case of column traversal, everything it's higher. For example, there are more cycles per instructions, there are more L1 cache misses, there are more L3 data load cache misses, and more data translation look-aside buffer misses. Now, what we have more figures, but we still don't understand the problem. However, we are getting closer to it. So in order to understand why those counters are different, let's get back to the theory and let's understand how a CPU works in terms of caches. On modern hardware, CPU consists of hierarchical layers of caching like L1, L2, L3. And for example, for L1, the data cache, it's split in cache lines. So each line has 64 bytes on the majority of the hardware. What happens when you request something from the memory, from the virtual memory, that piece of information is retrieved and it fills inside one CPU cache line. But not only that element, also the elements closer to that you requested are laid out in the same cache line. For example, if you request the first element out of the matrix, the next and the third and the fourth are laid out in the same CPU cache line until you fill these 64 bytes. Which means basically when you request the first one and then you move to the second and to the third, you have those ones already in the same CPU cache line. In comparison to the column-wise traversal, you basically request one element, you fill the entire CPU cache line with all the next elements, including the one that you requested, but then out of this cache line, you access only one element, and basically this cache line, it's evicted. So it's a very inefficient way of accessing these elements because you fill the entire cache line and request just one element out of it, and then because you change the row, you fill another CPU cache line, take only one element, and so on. So that's why the number of misses is more than for the column traversal than row traversal. And this explains also the figures, which leads me to the conclusion that you should be very careful also to the way you traverse those data structures, because it's not only about the BigO complexity. Also, the way you traverse those data structures and their layout in the memory counts a lot. So if you are predictable and if you rely on compact data structure, the hardware helps you really a lot. So the recommendation for you is basically to reduce the code footprint as much as possible and to avoid also the number of indirections or pointers between objects, because you mess up actually the CPU prefetcher if you have more indirections and your objects are not compacted. The next layer is about tactics, patterns, algorithms, and data structures. First one is caching. From an architecture perspective, the caching tactic is one of the easiest. You can easily take a cache and add it to your application. However, it's not easy to properly tune a cache, because tuning a cache needs a lot of understanding. For example, what is the data pattern that I'm using? If my cache it's tuned based on the read-write-through policy, which means basically all the data which is updated, it's synchronized with the persistence. Or maybe you can tune the cache based on the write behind or read ahead policy, which means basically the data it's asynchronously with the persistence. Or also the eviction mechanism. mechanism counts because, for example, the caches are limited. And the question is, what's the best algorithm to tune this from the eviction perspective? Is it least recently used? Is it least frequently used? Is it based on FIFO order? Also, the fetching strategy counts because if you have applications where the data is static, why shouldn't you use a prefetching strategy? Because you prefetch everything and you will maximize the number of hits. However, if you play with a lot of dynamic data, why not on demand? So basically, when you request it, if it is not in the cache, you retrieve it. And also, if you follow on few predictable patterns, why not configuring the predictive strategy? And also, if you deal with, for example, other quality attributes like scalability, be very careful because caches, if they are not properly tuned, they impact scalability. Because, for example, if you are using a local topology, it's not suitable. It doesn't scale a lot. So basically, in this context, you should go towards partitioned. And if you go towards partitioned, the question is, how many replicas do you choose? Because you also might want to be available. In my recent case, I was using a cache partition with 3 replicas because also I wanted to be scalable, but also availability was important. So it's very, very necessary to understand all of this from your application because, as I was saying initially, caches are very cheap to edit. However, it's difficult to properly tune your cache. Batching, it's another one. Batching, it's about minimizing the number of round-trip times by, for example, wrapping or bundling multiple requests and send those requests across the wire. However, if you use the cache only with this rational in mind, probably, the batch only with this rational in mind, probably you are not using it in a more optimal way. Why I'm saying that? Because to use the batching mechanism in an optimal way, there are more other questions. For example, what is my batch size in order to send it across the wire to the receiver to first not suffocate the receiver handling rate, to not flood the receiver, to benefit of the maximum bandwidth, and to keep a low round-trip time. Because if you maximize the round-trip time, probably the batching size it's not properly tuned. And here it's not a very simple problem to that, how to properly tune the batch size in order to benefit of the maximum bandwidth and to keep a lower round-trip time. And the solution comes from this algorithm. I really encourage you to read it. It's called bottleneck bandwidth round-trip BBR congestion control algorithm, which basically tries to tune the batch size to benefit of the maximum bandwidth and to keep a lower round-trip time. It's very interesting. And you can find the paper on this URL. The next principle on this layer, it's about designing asynchronous. Martin Thompson said designing asynchronous, it's a good recipe for performance. And I totally agree. On top of this, I would say if you can design also stateless, it's a good recipe for scalability performance. So if your mental model is towards asynchronous and stateless, and if the nature of our application or parts of it you can isolate and develop on this paradigm, you can easily scale a lot. Memory access patterns. There are basically 3 ways to access memory. The first one, it's about a predictable pattern. It's called strides. What happens, let's suppose you have an array, right? And you can access element by element. So in this case, you increment the counter for the loop with +1. So the stride is 1. And because you are very predictable, the CPU prefetcher can guess your next element and retrieve it. It's very similar to the way you traverse the matrix in a row fashion. The next way to to traverse the memory, it's about special. In case of special, what happens, you request something and the elements collocated are likely to be accessed soon. And this really matters because, as you said, that for example, you request something when you try to request the element which is collocated to it, it is already pre-filled in the CPU cache. So it's about still locality. And the third one is temporal. You can, for example, completely walk through the entire heap, and elements that you requested before are likely to be requested soon because they might be already in the CPU cache. And I created a short test, a short program. What I did, I created a long array of size 2 gig over size of long, and I started the Java virtual machine with 4 gig of memory, and in all cases the stride it was around 1 nanoseconds, which basically it's very, very fast, which means almost all the elements were in the L1 CPU cache, in comparison with the spatial, which is around 4.4 nanoseconds, and temporal, which is almost 10 times bigger than spatial. So this is another conclusion that you should keep into consideration, that memory access patterns, the data layout really, really impacts the performance. OS guidelines, thread affinity, it's a very cheap one. You can how you can configure, basically you have a thread, and if you bound that thread to a family of the cores or to a specific core, you benefit of the caches, because what happens when a thread is descheduled and scheduled on another core, possible on another socket, all of the caches that were pre-filled before are basically evicted. So bounding a thread to a specific core, you are still scheduled on the same core, and the caches that were pre-filled, you still benefit of them. So thread affinity, it's another technique to improve the performance. Non-uniform memory access says that the latency of accessing something for one thread, the latency to access one object from the memory depends on where is that located. For example, if this thread, which is scheduled on core 0, access an object which is remotely located, you need to pay the cost of this interconnect, the interconnect between these two sockets. And it's a very inefficient way. And the better way is, why not to access memory which is local to my socket? And this is non-uniform memory access architectures. In practice, you can basically bound that and isolate this to benefit of this local memory access. For example, for Java guys in the audience, unfortunately, in Java doesn't do a very good job in this way. It's just one collector. However, there are some Linux command lines that help you to do that at the OS level. So in this case, you minimize the latency of reading and writing from the main memory. Large pages. What happens, for example, when you want to access something from the main memory? There is also a translation between the virtual address and the physical address. And to do this translation, there is a short cache which is called translation leukocyte buffer, which keeps the latest translations between virtual and physical memory addresses. So initially, when you request something, the translation needs to inspect the TLB, and if the translation is within the TLB, it returns the physical address and it is requested from the main memory. However, if it is not inside the TLB, you need to walk the page and compute the physical address. And walking the page is very costly because it's hundreds of cycles in few cases. And here, to minimize this latency when we have the TLB miss, are two options. Either to increase the TLB, to increase the cache, to store more translations between virtual and physical, either to increase the pages. By default, the page, it's for example 4 kilobytes. However, you can increase it to 2 megabytes and so on. The first option, to increase the translation look-aside buffer, the cache itself, it's not very handy, because increasing the cache, you increase also the latency when you try to search something out of it. And the hardware providers are very, very precautious with the TLB number of entries. And the second option, which is more handy, is to increase the page in the OS. And this is the notion about large pages. Because increasing the page, you minimize the number of TLB misses. Why? Because more objects fall within the same page, so basically you have just one translation for all. And here it's a guideline when it's suitable for you to increase these large pages is suitable for intensive memory applications with contiguous memory access. And also when you do a profiling and the number of TLB misses and TLB page walks take a lot. And only in that situation you need to get and increase the large pages. Otherwise, I don't advise you to start directly with increases the large pages, because it's not recommended for small working sets or application with large but sparsely heaps. In this case, it doesn't work well. So be very careful. It's a technique that you should be careful with. And when you have applications that do a lot of I/O operations, but intensive operations, go to use RamFS and TempFS. Don't pay the latency of physically reading and writing to the file system. Write directly in your RAM, because it's way faster. It's suitable for logging, for auditing, for all these kind of applications. And here, what I did a short test. I sequentially tried to read and write 8 gig in chunks of 4K or 512K on my HDD, SSD, and RamFS. And as you can see, for RamFS, it was incredibly faster. It was like 10 times faster than SSD, and also SSD, it's way faster than HDD. So keep this in mind. You can rely on RamFS and TempFS for intensive I/O operations, because you increase a lot the performance. And the last one, it's about hardware guidelines. Hardware guidelines, first it's fault sharing. Fault sharing, it's basically a CPU issue. It's the way the caches are built within the CPU. And being conscious of that, we can prevent these fault sharing situations in our application. What might happen? Suppose you have a wrapper, an object which has multiple fields like X and Y, and multiple threads. Each thread, for example, thread 1 updates X, and second thread updates Y. If I would have to ask you, is there any contention between thread 1 and thread 2? The obvious answer is no, because thread 1 updates X, and the second one, thread 2, updates Y. So there is no contention. However, from the CPU perspective, it's a contention. Why? Because the way this instance, its layout in the CPU cache line, X and Y falls on the same CPU cache line. And when a thread writes something, it needs to get ownership for the entire CPU cache line. And getting the ownership, basically, all the other threads that have the same copy needs to invalidate their copies. So basically, when this thread writes something on X, it gets ownership first on this line and invalidates this cache line for the second thread. When the second thread needs to increase Y, it sees, okay, this is an outdated value. It gets ownership, it updates it, and then writes Y value. So there are a lot of back and forth messages between within the CPU just to update X and Y. However, from a programmer perspective, I would say there is no contention. How to solve that? It's quite easy. You just add some paddings between X and Y in the way they don't fall on the same cache line. So if they don't fall on the same cache line, there is no fault sharing effect anymore. for the programmers, the pattern to identify the fault sharing, because it's not easy. If you profile the hardware, it's not easy to catch the fault sharing. However, from a programmer perspective, you should identify if you have variables that might fall on the same cache line, and those are accessed by different threads, and the access is concurrent, and you have at least one writer, there is a fault sharing situation. And also the frequency counts, because if the frequency is high, you will suffer out of the fault sharing. Even if you have concurrent access but with a low frequency, there is still fault sharing, but you probably don't notice it. So be very careful. You should know this in advance. You should know how you create your data structure, how it is accessed, which thread writes and reads, and with each frequency, because in this case you may end up with a fault sharing problem. And the last one is about SSD. We all are using SSDs on our boxes. However, for example, in Linux is not properly tuned for SSD. Why I'm saying that? Because first, you should take care of the trim command. It comes by default as being disabled. However, my advice, if you are keen on performance and you have an intensive I operation, it's better to activate it, to switch it to on. What trim does, actually, when you want to remove something, if the trim is off, it is just marked on the SSD as being deleted. And later on, when you want to write something, the SSD needs to find blocks, all of full of chunk information, and scrub the entire block. However, if you have on activated, the information it's removed at that time when you remove it from the application, and you don't suffer the latency paid later on to scrub the entire SSD block, because the SSDs cannot physically remove just that particular information. It needs to find available blocks of 512 kilobytes, for example, and scrubs the entire block. So if you activate trim, this doesn't happen, and you write information quicker. And also the I/O scheduler. On Linux, there are 3 I/O schedulers, not in all distributions. For example, Ubuntu comes with 3 I/O schedulers. And the I/O scheduler is also very important, because by default, I don't recall, I think it's dedline, the one that comes by default. However, I did some tests, and the noop scheduler, it's the best one in terms of throughput. The noop basically uses a FIFO, and it merges the read and write requests. So with this noop scheduler, you benefit out of the maximum throughput. And also, if you activate the trim on, it's even better. So my advice for you is to take care how you properly configure the Linux boxes, because you should take care of trimming and the scheduler itself. And getting back to my latency model, now what we can map in it, if the performance is not an ASR, basically keep on writing small and clean methods, pay careful with the psychometric complexity, cohesion matters, number of abstractions matters. If the project is somewhere in the affordable latency area, you should properly choose your data structures, pay careful with complexities. Why not using batching, caching? For the low latency, memory access patterns matters. Why not try to use asynchronous, stateless processing, RamFS, TempFS? And the last one is ultra low latency, where you can do all the others. So thank you very much. Just before to close, I would say performance is simple. You just have to be aware of everything depending on your project. Thanks a lot. Questions, please?
So you mentioned a lot of concepts around profile, but what tools do you use?
I personally use Perf. Perf on Linux is a great tool to do CPU profile. On Windows, I think it's not quite handy. It's VTune, Intel VTune, and also EMD has some software. But in Linux, it's very easy with the Perf command. So I'm using Perf.
EPF?
Yeah, but I haven't used it. I think that one is based on Perf as well. Or use Perf? No,
It's actually below.
below Perf. Okay. I haven't used it.
You know Random Dragons?
Yes, it says, yeah, I
It's one
know.
of
He has a lot of such tools,
Yeah.
but I haven't used it. Nothing from Random Dragon.
What's the average performance improvement that you expect to see after the next speed profiling?
Sorry, what's the?
The average speed performance improvement you expect to see in a real life application? I mean, what as a recommendation to software developers, when would you go in and ask your sysadmin, which would be Academy, go in and do CPU profiling on their production environment and expect them to do something on your behalf, whereas you can do it.
Yeah, my advice
is
is,
the application before.
yeah, it's to do it like the last solution because it's the most difficult one. When you profile the CPU, it's most difficult because you can end up with, for example, big counters, and the question is how do you interpret those counters? Where the cache misses come from is not very easy to, for example, when you do CPU profiling, can you say, oh, I have a lot of CPU cache misses. How can you associate them with your source code? It's a difficult way. So I would say that the last solution to do that. If you are also on the ultra low latency stuff, it's really worth to do that. But unless just for fun, I would say, because it's very, you need to understand the SMD, you need to do a lot of things.
The problem is we do track those in our performance management tools, but we cannot report them back to the developers because they're meaningless. What I can tell my developers is from 1 release to the other, we fuck off.
Yes.
We increase the security misses for some reason.
Yes.
Cache misses or something like that. But outside of that, I can't really pinpoint it down further than that.
No, and it's more suitable for micro benchmarks, because if you do macro benchmark and you have frameworks, you really are lost. So I really advise you to do in very small pieces with micro benchmark. And also what you can do is to bound the threads to specific cores, to isolate those cores for the CPU, other OS threads to be more predictable. But still, it's difficult. I mean, you really need to, as I was saying in the end, you really need to be aware of everything.
How do you design your programming components in order to fit the memory layout to not have cache misses? I mean, besides arrays that are a continuous flow of memory.
Yeah, from a programmer perspective, it's very important to really use the appropriate data structures. It's very important because also from practice, a lot of performance issues comes for misusing the data structures. Misusing the data structures, misusing the threading models, misusing the queuing models, and all these kind of issues that are more tangible for us than the programmers. And if I would say, if you do all of this properly, you have better chances. You don't really care about the CPU and all of this stuff. Unless you, for example, design ultra low latency trading systems like LMAX guys. LMAX guys did almost all of this, but it's the most performant trading system. But unless for the majority of the projects, because also I have some recommendations for you, RPA. For the majority of us, what I advise you to read, it's Ulrich Draper has brilliant articles about understanding the memory, the CPU caches, the NUMA systems. By the way, you shouldn't be an expert of understanding hardware, at least you have to know the basics. And these articles are about the basics, and you will understand really a lot. And also data structures and algorithms. If you know this, you definitely write that code. You shouldn't know assembly. Really, you shouldn't know assembly. I do assembly for fun in most of the cases because I like that, but you shouldn't do if you follow on these guidelines. And if you do a proper profiling at the application level, at the OS level. And also, what's here very nice is Kurt Perpendine have a performance methodology, MindMap, and also Scott Mayer. Scott is a C++ guy. He has a very good talk with CPU caches and why you care. They are very good talks. You can search offline and watch them.
Can you give me an example of how of a situation when you go down from an application that you plan it into a framework and you have go down until the assembler code because it's huge code?
No, I never did that. I usually what I did did only when I know the target it's assembly, I isolate and I profile only specific data structure and specific algorithms, but I isolate them from the framework. If you have the framework, it's almost impossible. Because also the framework is compiled and you don't really. And also if you are Java guys, it's even more difficult than in C++ unless you are using STLs. Because there is a lot of pointers in directions and all the JVM does a lot of things under the hood and blurs the assembly. It's not so easy unless you know the logic in intermediates. But other than that, to answer the information, I never did that. And if I have to do that, I really isolate. And then by having it in isolation, I can easily read the assembly. With the framework, it's impossible.
Just curious.
No,
I
don't
did some
think so.
assembly
Yeah,
when I was in college, but
yeah, it's very difficult. At least you can end up basically at the number of CPU cache misses or transaction side buffer page walks and misses to activate the large pages. That's it if you are using frameworks. Because also you have really fun stuff. So it's also not recommended. You can use for it. Yeah, the quickest one is to enable large pages if you decide it's a need, to do thread affinity. These ones are very cheap. But more than that, to touch assembly, it's difficult. And it's impossible.